who runs this company, which is a Xeon Phi based technology. It's a machine, it's a liquid cooled machine, got some nice networks in it, and helps inter card communication, etc. Now, let me see. So this project was actually an IPCC that was centered around the games code, the General Atomic and Molecular Electronic Structure System. As you know, this problem is kind of interesting in that with a lot of matrix problems, you have perhaps an order n square setup and an n cubed kind of solve step. Has a setup of order n to the fourth and brings in some complexities that need to be addressed. The code base itself is from the 70s. It's kind of written in an old style. It's got a lot of methods in it, and it's got a lot of users as well, by the way. That brought in some challenges. MPI only in the official. Our challenge was, what do we do? One thing that popped up really quickly up front was because it was MPI only and there was lots of replication of data, we hit this, issue of basically running out of memory on KNC and, of course, running out of MCD RAM on KNL. And that to us wasn't something that we wanted to give up too easily on, right? So we looked at the threading of this code, and Yuri will give the details. Our strategy, of course, was to do the threading first and then set ourselves up so that we could do the vectorization of the electronic integrals. Yuri, do you want to bring it up? Come on, yeah. As far as this IPCC project goes, one of the nice features about it from a programmatic point of view is that we were able to actually tie in several IPCCs and bring in some resources from Intel beyond what was offered in the traditional IPCC framework. So if you find yourself in a situation where you need that little bit of extra help, we can actually help make those connections and actually do it very profitably. In this case, it was particularly nice because I live here in Chicago, and Yuri was a great guy to work with, and we were able to hole up in a room and just kind of get things done. But similar arrangements can be made elsewhere as well. All right, so I'm just going to hand it over to Yuri, and so he'll tell us about all the details.
Thank you very much, Michael. All right. Thank you very much, Michael. So I'm going to talk about parallelization of the games. And this work is done in collaboration with Michael from Intel and also with two scientists from Moscow State IPCC, Vladimir Mironov and Alexander Moskovsky. Vladimir was actually a programmer, and he did most of his work on programming. Okay, so first, a little bit of introduction about games. Games, by the way, it's not because we play quantum chemistry games. It's actually acronym, okay? And this is introduction for Hartree-Fock. In Hartree-Fock, we are solving a molecular Schrödinger equation. It's called ab initio method, but in reality, and it stands for from the beginning in Latin, but in reality, we make a number of assumptions and approximations. Just a few of them. First one is Born-Oppenheimer approximation, and this is basic assumption that nuclei are fixed and electrons move very sparsely, and this is later determined. This is antisymmetry and the introduction of basis sets, and this is Alcao approximation, and this is approximation for wave function. In the molecular Schrödinger equation, so this is Hamiltonian, this is operator, And this is which describes all interactions in the system. This is wave function, and this describes the state of a system, and this is the energy. After all these approximations, you end up with Ruffin equations, and this is what you solve. And so F is actually a matrix representation of the Hamiltonian. C with the coefficients, and this is for represents wave function here. This is overlap matrix, and this is energy. There are slight issues here. So first of all, you don't know actually how the wave function looks like. You don't know the energy of the system. And you have some ideas about interactions with systems. These are like electron-electron and nuclear-nuclear type interactions. But F function itself depends on wave function. And so how do you even start here? What you do basically, you make an initial guess, density matrix guess. And what you do, you solve this equation iteratively. And you solve it until the density converges. All right. So it's, as you can see on the previous slide, it's all about Fock matrix computation. So how do you compute that? I see there are some issues here. So it's basically electronic form, and what you do, you compute these two electron integral repulsion integrals. They are by far the most expensive part to compute, and we scale as n power 4. And this is the formula. Yeah, on my screen it actually looks quite different. And it's really glorified Coulomb repulsion between two electrons. You have one electron on one side, one on the right side, and this is just the distance between them. And this is quantum chemistry, so actually this electron can be located on the two orbitals, I and J. So a few observations here. First of all, there is a symmetry here. You can actually, because of symmetry, you actually compute, each computed integral actually updates 8. It has 8 updates to Fock matrix. And the second observation is actually very expensive. So what happens every time you just even add like one atom? These interactions are, by the way, this is like all-to-all kind of interactions. So it's a complete enumeration. It becomes very expensive very fast. And by the way, this is one of the cheapest methods in actual quantum chemistry. Our methods actually scale like as n power 5 up to n power 7 actually, or even more expensive. The Fock update it's very unique, and it's actually very funky way how it's done. So each integral, IGKL, you need to multiply by density, which is DKL, and it updates IJ. And you can see, after that you take this integral and multiply by IJ and update scalings. So for the compiler way, how it looks like, you take a basically constant and multiply by a random density array element, and which updates another density update element, array element. It's actually very hard to vectorize, and it's actually one of the issues of quantum chemistry. Okay, what kind of challenges we have, and what kind of solutions we propose? So about games, it's monolithic code, it's huge. It's actually roughly 2 million lines of code. Written ages ago. It says it's not actually written 1477. I think it predates even 1477. And it's optimized for all CPU architectures. Well, in 70s and 80s, we didn't have cache. So it's not about that. It's all about minimization of flop operations. There are lots of global structures. I'm talking about common blocks. The whole code is riddled with common blocks. They're like used everywhere. And these common blocks are used mostly to pass a vast number of variables. There are lots of obsolete constructs. Nobody uses them. My favorite is actually computer go-tos. We have our own dynamic array allocator. And what it does, it basically we just have a fixed array and we just move the pointers ourselves and compute upsets. And so what happens, because of that, debugging is actually a nightmare. it has, and quantum chemistry in general has high memory demand. So why we care and why we still work on this code? This code is like 4 decades in development. We recently estimated that we have over 200,000 users worldwide, lots of active code developers. There are 2 spin-offs of this code. And in general, it's one of the most popular quantum chemistry packages. Why LCF cares? We usually have at least one inside. We participated in all early science projects. We're also part of exascale computing. And we have currently 2 IPCCs. One is located at Moscow State University, and now one is located in Iowa State University. So what kind of solutions we propose? We're actually under transition right now, and we're converting Fortnite 70 code to Fortnite 95. We remove global data structures where it's possible. And in this work, what we did vaporization and some vectorization. So this is the Hartree-Fock, and this is way how it's implemented in games. There are different types of implementations of this. So you remember these 2 electron integrals. So you see these indexes I, J, K, L. The formula which I shown before, it was for atomic orbitals. This is actually for shells, and it's actually very common to loop over shells around actual basis functions. It's done for multiple reasons because of screening and way how integrals are computed. So way how it's done, you have total number of tasks n power 4. And so what you do, you loop over J index, and this is where dynamic load balancing is located. And so what happens, each MPI rank computes its batch of integrals, computes each share of Fock matrix, and after it's all done, you basically reduce the Fock matrix across all MPI ranks. All right. So how we implemented threading, OpenMP threading? It's quite complicated. So first of all, what we do, we sort the shells. There are a couple of reasons why you're doing this. This is for load balancing, and it's one reason. The second reason, it actually helps a lot when we compute integrals. We compute integrals in batches. If you sort shells, it automatically implies that you need to sort the density matrix, and automatically implies that the Fock matrix is going to be wrong format as well. By the way, these matrices in the games, we are trigonal. We actually convert them to square matrices. And after it's all done, we actually see at the end we need to repack Fock matrices and bring back to the original order. And this is to make sure that the rest of the games doesn't break. OpenMP parallelization done, initialization is done outside the loops, and it's here. And all MPI parallelization is done over I loop. And you can see OP duo here, all the threading done is done over J and K indexes. And for L index, we reserved it for batching. So all integrals are shell quartets. We actually computed in batches, like in one go, and we use L index for that. So this is Schwarz screening here, and we compute integrals. So, and once it's all done, you need, it's also worth to mention that the density matrix here is shared, but the Fock matrix is actually replicated. So how do we scale? So first of all, what is the thread affinity impact? As you can see on this picture, you have compact. We tried different types of affinities, compact, balanced, scatter. And as you can see, it's very predictable that balanced and scatter perform the best. And for the rest of the code, we actually use balanced affinity. So the code scales up to 240 threads, no problem. And this is a version of Xeon Phi which we used to run the tests. This test, by the way, is done for graphene bilayer, 60 carbon atoms. This is the base set. So this is the scaling of OpenMP and MPI on a single Xeon Phi. So this is the data for this figure on the right side. One important, what I really need to mention here, so on machine which you run, it doesn't have a lot of memory. DRAM, it has only 8 gigabytes of memory, and we with MPI, we had major issues. Even for this small system, just C60, it just could not fit in memory. So what we did, we ran with MPI, we ran out of memory on actually on, it should be on 52 MPI ranks. OpenMP code, as you can see, it scales just fine, and they're actually very comparable. And on 32 MPI, 32 threads and 32 MPI ranks, you can see the timings are very close. But OpenMP code can scale up and it can fit in, and we didn't have issues even to run it with 240. And in fact, we actually have seen even scalability beyond 120 threads, as you can see. All right, so this is another graph, and this is very similar graph. By the way, these figures, I was being lazy, I just copied and pasted from our supercomputing paper. And so what we have done here, so this is what you do is it's a single Xeon Phi, and what you do, you increase number of cores, and each number of cores, what you do, you vary number of threads per core and number of PI ranks. And you can see basically the code scales, both OpenMP and API, we scale just fine. And in fact, this OpenMP code with one thread per core actually scales slightly better than everybody else. Okay, so this is the scaling of the code across multiple Xeon Phi nodes. And in this machine, and this is machine from Petasty machine, RSC, from Russian University. And you can see here that we didn't have any issue scaling with the 128 nodes. And MPI scaling it scales, but time to solution is quite horrible. If in fact, this is log scale, and you can see for OpenMP code, it takes on single node, it takes 600 seconds. The same code runs about 6,000, actually, over 6,000 seconds. The reason is because the system is bigger, and we just could not fit in memory. So this is actually, MPI runs very, very inefficiently here. About OpenMP, why it flattens and doesn't scale beyond 64 nodes. This is for, in general, because this is actually a fairly small system. It just doesn't have enough really tasks to scale up to like to larger number of nodes. The original code, so in our issue, which is very interesting issue with API code, we actually, API code could not even run beyond just a few nodes. We needed to actually use double feature to make it work. And this is InfiniBand's feature. But OpenMP code did not need any tuning. All right. So preliminary results on the kernel. So this is for electronic propulsion code developed by Vladimir. And so this is a figure which actually has two parts here. So this is old original code, and this is running on KNC versus kernel. In our benchmarks, you have seen the for both. This is L, here is the angular momentum. In general, the old code runs about 2 times faster compared to KNC on kernel. But our new integral code, I didn't talk a lot about this, but it's also under development. It actually runs roughly 3 times faster. And there is also work underway to increase data vector length. All right. All right. So what I did, I copied this table from Microsoft Word, and it didn't copy correctly, I guess. So this is from our Aurora ESP proposal, which we have written about work on the mesoporous silicate nanoparticles, they're called MSNs. This is a fairly big system, almost 2,000 atoms and a huge number of basis functions. We didn't have a lot of time, but we ran the code on Feta. and we run non-threaded code actually. And this is for 64 MPI ranks per node in the cache quad mode. And these are just preliminary results. I looked at them like a few days ago, and I was actually got very excited about this. So first of all, if you run, as you can see, so you need to look at the speed up. As you go from 148 nodes to 156, it's actually 2 times speed up, which is actually what you expected, what you expect. But as you go to 512 nodes, I thought that is going to be number is going to be close to 4. But what we got here is actually almost 5. It's just under 5. And I think this is very interesting observation. Other speakers didn't talk about that. But I think on Theta, the codes which actually use like large data structures, you can see it. As you can imagine, as you increase number of nodes, the data shrinks. And it's actually much easier to cache the data. And in ideal scenario, it will just fit in an MCD-RAM. And this is the case when you may see this superlinear scaling actually. About the results, so now the editor repository code is thread safe. We implemented OpenMP parallelization. This is done in the CF driver. Memory reduction was done. We threaded the code. This is energy code and gradient code, and we have done this for all kinds of wave functions, restricted Hartree-Fock, restricted RHF, and also DFT, hybrid DFT. I'd like to acknowledge use of Argon LCF resources. Vladimir acknowledges we use IPCC, and we also thank St. Petersburg State University, Polytechnical University for providing computer time. And all Theta benchmarks were run by Christopher Kuiper, who is a graduate student from Iowa State University. And thank you for your attention. So, any questions?
Showed the speed up of KNL relative to KNC. I'm just curious what difference you see between KNL and the Xeon.
So Michael is not. For all kinds of reasons, it was a bad idea to publish a paper where you have benchmarks, especially the Intel employee, where you actually compare different hardware. It was by design. We actually did everything on KNC to avoid these issues. But in general, KNC code runs slower compared to Xeon.
Just because of some parts of the code that you haven't yet gotten around to parallelizing, or?
Well, this code is memory bound and latency bound, and way how you use the cache is super important. And we had all kinds of issues on KNC. One is very unusual. This is for Schwarz inequality. What you need to do, you need to compute these exchange integrals. And this is essentially at the time when you compute actually integrals and reduce Schwarz inequality, you need to look at the tables. It's like lookup table, and this table is quite big. On KNC, it was actually most time-consuming step. It's on like on regular Xeon CPUs. I have never seen that.
Question regarding the timings of your calculation on the silicate. So are these wall clock times for the full solution from scratch or per iteration?
When we actually do these benchmarks, we just do like one SCF iteration. Yeah, it's usually representative actually, because it's not like real research project, right?
Okay, there are no questions. Thank you again.
Right, thank you.